zinger that I have built up over the weekend. Yeah. I'm telling you. Like not even my mom would watch this stuff, right? She thinks I'm awesome. But she's also biased, so I am the favorite son. Huh?
Your number one fan, your mom.
That's true. That is a mom's job, right? Very serious.
Yeah,
So
they take it real seriously too.
yeah, and that's good, right? It honestly is. Anyway, so although where was I? What was I talking about? So when we were doing in class, right, we were working our way through the electrophilic aromatic substitution stuff, right? And we got one more of the same thing that goes up to the exam for Thursday, right? So the stuff that we're going to learn today will still be on the exam. But it's just, I mean, honestly, you get, like I said before, and I've made the joke and I've talked about all these things, you guys already know all the mechanisms that's on this in this chapter, right? All it is individual bits and pieces here and there, right? So anyway, what we were discussing though is the idea that we have to generate an electrophile. And while we learned how to use the aluminum chloride, or the aluminum chloride there to react with an alkyl halide to generate a carbocation, right? We said that essentially any way that we could generate a carbocation is a potential way of adding an alkyl group to an aromatic. Now the difference is if I use a strong acid, right? If I use a strong acid like HClO4 perchloric acid, then that's going to react with anything in there that's going to act in remotely basic, right? The difference is if you use AlCl3, right, it's going to be a little bit more targeted towards halides. Well, not a little bit more, it's going to be very targeted towards halides. Although there are some other functional groups that it can cause problems with. We can have a couple issues with alcohols and things like that around. Although for our purposes, it's not really going to be a big deal, right? So, but I'm just letting you guys know, sometimes the book, not sometimes, often the book leaves a lot of things out, right? For good reason. If we wanted to sit here and just spend the entire rest of the semester talking about EAS, then we could, right? And I would get bored after about 2 days of it, and you guys would also, right? But there is a lot of nuance that goes with it. But again, just to kind of keep reinforcing the same thing that I talked about over and over and over again, there is the reason why we pick some reagents over the other one is to afford some kind of selectivity towards specific functional groups, right? So we have to pay attention to what we're doing with it. But at the end of the day, we learned 2 good ways of adding alkyl groups. We did the Friel-Crafts alkylation, right, where we have an alkyl halide and we have the aluminum chloride, and then we talked about when we have an alcohol and the boron tetrafluoride, right, the BF3, right? So we have good, excellent ways of adding alkyl groups, although they do come with a problem. And what's the problem with both of those mechanisms? Or maybe not problem, or concern. Yeah, anytime we generate a carbocation, what do we have to do? Rearrangements, shifts, all this kind of stuff, right? So we have a problem. We want to generate a carbocation because we need a good electrophile, right? But we need that carbocation not to rearrange and not to shift, okay? So we have to have a specific set of conditions, I guess, that are kind of met. And so what we do with that then is my computer's looking at me, Joe. Yeah. All right. I don't know what's going on. Not that I really tried to fix anything. I guess, serendipity I thought was going to happen right now. So, I did restart it twice. So now we go to Friel-Crafts acylation. Right? Okay, so first of all, what's an acyl group? An acyl group, we'll see this quite a bit, especially coming up in the subsequent chapters. Right? Okay, so an acyl group is a kind of carbonyl group. Right? You see the C double bond over there. On one end, we have a carbon, the R group, although we could have a hydrogen, although it's very, very, very uncommon, right? And kind of very not really ever going to be practical. So for all intents and purposes, the R is a carbon group and the X is a halide. Okay? So we have acyl chloride or acyl bromides are what they would be called. Right? And they're going to have a lot of purposes for us. Now, one purpose is what we're going to learn here. We're going to use them to add an alkyl group to an aromatic ring. Okay? Now, what do we know about chlorides and bromides? How much chemistry have we talked about with those? Yeah, right? Now, do you think they're going to behave all that differently here? Yeah, right? So if we take Mr. Generic benzene ring, sounds good, okay? And we take Mr. Generic acyl chloride, okay? See what you guys can come up with. What, you guys are all making primary carbocations? No. Primary carbocations, huh? Now everyone's nervous. Yeah, like, No. I mean, if you did that, what would happen to the formal charge actually? Would go up, right? So I need to eat some lunch. All right. I know. Yeah, no, I don't want to keep carrying 5 pounds over here if you guys want to answer one question a day. It's your birthday. Well, happy birthday. All right. Nobody joined in. Feel like an ass. All right. Here we go. Do you want to be on camera? Yeah, this is her birthday, right? Well, the YouTube bot watches it right now. Anyway, so, but happy birthday. I'm sorry that you're stuck here. This seems like the worst present. So, now anyway, we do have our Lewis acid still, right? And we know that the halogen is going to be going after that aluminum. That sounds good. And so when we do that, we weaken the chlorine-carbon bond, right? And if we broke that chlorine-carbon bond, we would end up making a primary carbocation, right? You guys with me on this one? You guys following along in the theater of the mind, I guess? Right, essentially this, and then if we broke that, which remember, you guys can do this in one step, right? You can show that in one step. And essentially, what we would have is this, right? Right? Yeah. What if I told you that's what happens? Alright? Now remember, all along, I did tell you guys what? Well, not only that, but we'd be sort of making a primary carbocation, right? Now, by our definition, this would be primary, since we're just looking at how many carbons is that one carbon attached to. But what's different about this? There's resonance, right? So this is a resonance stabilized carbocation. Do you guys see the resonance? Are you sure? Can you draw it? Can you copy off your neighbor who drew it? No, Dr. H, my neighbor's a dum-dum too, right? Yeah. I didn't say who. You guys are pointing at each other now, right?
That's what he's thinking about.
Oh, okay, good recovery there. Alright, right, so all I'm saying is we could draw a resonance structure like this, right? Weird. You said this weird looking resonance. Is that a resonance? Yeah. What is that effectively doing? Stabilizing it. So is it going to want to shift and rearrange, move? No. Right? So there it is. It's going to stay there. Nice. Right?
Dr. H, what if like the R chain that was coming off of it had something else attached to it? Would that affect the carbocation?
Would it affect it? Yes. Would it make it shift? Probably not. There would have to be some significant shenanigans for it to move away. So, just to clean things up, right? Now we have this, which is a good what? Electrophile. So what happens next? It does the electrophile thing. Ladies and gentlemen, if you want to see progress in education, I think what she was trying to say is that it continues on with the rest of the mechanism at this point in time, right? I'm just going to fill in the blank for you. Don't worry, they only see the back of your head. It's okay. Right, so it goes on and continues with the rest of the mechanism is what it is, right? So we have a nice electrophile. It is resonance stabilized, right? But it still is a carbocation, right? So it's going to get attacked by the pi bond of the ring, right? And then we go through and reform the ring again, right? Good. Right. All right, there it all is. Cool. Anything different? Nope. All right, we still have the halide, which attaches to the Lewis acid to generate the electrophile, and then the electrophile gets attacked by the pi bond, and then we reform the aromatic ring, right? Good? Now, what functional group did we end up turning this into, in essence? It was already a carbonyl. A ketone, right? You should have just said it louder.
I said it first thing.
I know, no, I just.
I said first thing went wow.
No, yeah, I thought I heard you say ketone first.
I did.
Yeah, that's what I'm saying, just say it louder.
I had the same thought.
Ah, nice. Okay.
I just like you take the fall first.
Yeah. I want you to sound dumb first, and then I'll take credit, all right. So, right, we ended up making a ketone from an acyl halide. Now, this is a special kind of ketone because we are adding it to an aromatic ring, right? But we do have a transformation, I guess, from one carbonyl group into another. Now, we're going to talk a lot more about those kind of transformations in a couple of chapters, right? So that'll be coming up. So, but there it is, right? Great, fantastic. But we still have a problem, right? Because let's say that I wanted to do this. Right, where I wanted to, let's say, add a butyl chain to an aromatic ring. Okay? Now, what's the problem, right? What's the problem with the reaction that we're trying to do here? So we have an aromatic ring and we have to add an alkyl group to it, right? But where do we add that alkyl group? We add it to what?
All these carbons are equal.
Well, we add it to a carbon that's primary, right? Do you guys see what I'm saying with this? We add it to a primary carbon there. You guys catch what I mean? You see where the carbon that's connecting to the aromatic ring is, right? So we know we have to make a good electrophile from carbon. That's the only good electrophile from carbon that we know of. Carbocation. Will we ever make a primary carbocation? No, right? You guys see, that's what I mean by what the problem is, right? We can't really, and for all practical purposes, we can't really do this. Where we just say, no worries, Dr. H, just do this, right? Life is easy. What's the problem with this? Well, we're not going to generate a primary carbocation, and if we do, it's going to shift and rearrange over, right? So we can't do that. Dr. H, you don't understand. I read the book, right? And I can do this, right? Can you? Sure, right? That's not a problem. But if you do that, you'll end up making that right there, right? So we need to get rid of an oxygen. So what do we need to do? We need to replace carbon-oxygen bonds for what? Carbon-hydrogen bonds. So what type of reaction is that?
Reduction.
That's a reduction, right? So there's two types of reductions. They don't talk about them both in this chapter. I really don't know why. But we'll go ahead and talk about both of them here because I make the rules. Yeah, that's how it works. All right. So we have two types of reactions. Now, both of these have their time and their place, I guess is what it is. Okay? First, the one that they do talk about in this chapter. There it is. Okay? Take some zinc and mercury. Alright. So if we do this, what we will end up doing is getting rid of our carbonyl. Right? And so this right here is our two M's. Yeah. Clementine Reduction. Okay? Clementine Reduction takes our carbonyl, we get rid of it, and we leave just the alkyl chain behind. Okay? Zinc, and then in parentheses, mercury. Ooh, what does that all mean? Mercury is a super cool metal, and there's some fantastic videos on YouTube about this stuff, how mercury likes to make amalgams with different metals. Like, I'm pretty sure it's mercury and gold. If you go look at the videos for it making amalgam, like the mercury literally, like it looks like it's just dissolving the gold. It looks like it's eating it almost. It's amazing the way it works, right? But mercury is a very unique metal, although we don't use it too much. Why? Because it's kind of bad for you, right? So, and then we have to dispose of it, and it costs a lot of money to do all these kind of things. But here is probably one of the quintessential reductions, one of the first ones that was kind of discovered. You make a zinc-mercury amalgam, and you add in some HCl. Now, if the stuff comes in by next week, right, we're going to do a similar reduction, sans the mercury, right, to maximize student survivability. We'll do a very similar reduction. Now, HCl, or let me back up here for just a second. So this is going to reduce the crap out of most things, is what it is. All right. It'll get rid of those carbonyls, but it'll go after a lot of other functional groups too. And in fact, we're going to use very similar setup to do a reduction of nitros. Right, and I'll talk about that in just a little bit here, right? But this will kind of reduce everything for you, but it'll get the job done, right? So zinc, mercury, do we need another mechanism? No, right? So, did I read your mind? Yes. Right? There it is. We got a problem though, not too selective. HCl is going to go after a lot of things. That zinc, mercury is going to react with quite a few different things. So not too selective. So there's actually one that is a lot more preferential, and that's actually called the Wolff-Kishner. Very German. Wolff-Kishner reduction. This is the one I prefer because I have German heritage, of course. Right? Let me look this up real quick in the book. Where this is for you guys, I think it's in like chapter 19 or something like that. Where is it?
Is this going to be on the exam set?
Yeah, that sounds good. Page 867. So chapter 19, I was right. Cool. Did I even spell it right? First day teaching, I haven't made any mistakes yet, all right? So Wolff-Kishner reduction works in two ways. First, we use N2H4, okay? Now, what in the world is N2H4? Now, N2H4 is our buddy hydrazine. Okay? And we'll see it used quite a bit a little bit later. And then we come in with some base and we heat it up. Not too much, just give it a gentle little oomph to make things happen, right? And what this is going to do is it's going to effectively do the same thing for us, right? Now, what's different about the Wolff-Kishner is that we actually will learn this mechanism later, okay? So I'm going to hold off on that part of it. But it's useful for us here. Why is this useful here for us? Well, first of all, the Wolff-Kishner reduction is going to be a lot more selective. The first part of that, the hydrazine, reacts specifically with carbonyls. And what we will also learn is it's only going to react with certain kinds of carbonyls. Okay? So it tends to be a lot more selective. There's no acid around, right? So we don't have to worry about things getting uber protonated, right? But they are under basic conditions, so we do have to be careful about other things that are acidic, right? So if we have a carboxylic acid group around, then we'd have some problems trying to do a Wolff-Kishner reduction. Maybe, right? Maybe, this kind of depends. But this is another fantastic way that we have of getting rid of our carbonyl group that we make there. Okay? Good? So we'll come back and learn this mechanism, but not now. So what part of this is on the exam? Just know the setup at the moment. Right, that's all. Good? No, too much information. Brainful thinking. What is it? Only 6 chapters on the exam, right? Is that what it was? 7?
No biggie.
Yeah, whatever. Look, I've never lied for you guys. What do I expect you guys to know?
Everything.
See? What, I gotta keep repeating myself? Cool. All right, so all joking aside then, so all joking aside, that'll be the end of the stuff on the exam, okay? So now having said that, let's talk about the next exam, all right? No breaks. So what we have to take care of next then is this issue. So every problem that we've done so far, I start out with good old benzene, right? Nice, simple, like easy, boring old benzene, right? Now, how often are we going to do that? Well, not too much, right? You know, benzene, there's not much use in it, right? So let's spice it up, all right? Let's say I start out with nitrobenzene. Indeed, right? Well, let's say I did this, you know, just to really shake things up, right? So I want you guys to see if you can figure out what the product is going to be. I'll give you a hint. You gotta draw it all out. Okay? That's a big shocker. You guys have to draw inorganic chemistry. And after you draw, what do you have to do? Right? I know this jerk is trying to trick us somehow. How's he trying to pull this time? Aha, it's from a different chapter. No, no, I'm kidding. No, this is all part of the chapter. So to help you all along your way, let's pause and make a quick assessment, right? Assuming that we only add 1 chlorine, right? How many different products could I make?
1.
Could I make? How are you getting 3? How'd you get 1? Well, Dr. H, I like odd numbers. And the first thing that came to mind. How'd you get 1 and 3?
I mean, you never said that the reaction couldn't happen.
No, I'm not telling you the reaction will happen.
Yes.
Yeah. So assuming a reaction happens, how many different products could you get? So let's back up for a second, okay? So scroll back in your notes there. I said scroll, not flip pages. Right? So look back in your notes. What are we effectively doing with every EAS mechanism? We're substituting what on the benzene ring for a new functional group? We're swapping a what? hydrogen for a whatever other function. Got it? So, still looking at your notes, okay? I just got plain old benzene. How many hydrogens are on there? 6, right? So in theory, you should have 6 different products, right? But how many do you end up making? Why? Because all 6 of those are identical. You guys got me on this one? Right? Okay, so make that same assessment here. How many different hydrogens, aka how many different places on the benzene ring do we have?
5.
In theory, we have 5, right? You guys with me on this? But how many of those are unique? 3. You guys with me? Where are my unique? Right? So just moving clockwise, right? Or counterclockwise. You guys see how both those oranges are the same, right? Yes? Right? If I add something either to either of the orange carbons, that would be the same product. Right? That would be my ortho substitution. Right? If I added to either of the green, I would end up making the same product. That would be a meta substitution. If I added to the black, it would be para substitution. Okay, now that we have that, so now you guys have 3 options for products that could get made, right? So draw your mechanisms leading to those 3 products. Go ahead and draw your 3 mechanisms. just to make life a little bit easier, is generating the electrophile going to change for any of these mechanisms? No, right? So if you guys want to shorthand and just start with Cl plus, right? That's fine. Should you do that on the exam though? No, right? But while we're learning here, right? If you want to start with Cl plus, go for it. Get to that. That's what I'm asking. And this is you showing a bond happens between the pi bond and that chlorine, and the chlorine magically disappears, but poof, that's back, right?
Yeah.
Yeah, so just be careful. You got the right arrows, just show the right arrows going to the product, right? Careful where your positive charge is. You don't generate the positive charge where you add the chlorine, right? So what if I told you that was the only one that formed? How can you explain that to me? So start thinking about that. So what if I told you that was the only product that formed? How would you explain that? And be careful, you're not going to add two of them. We don't know quite why yet, but take my word for it. You're only going to add one chlorine at a time.
Two.
You've got two chlorines on there for some reason?
Yeah,
You're not going to do that. You're only going to add one at a time.
but this wouldn't be a product.
No,
Okay.
but we don't know quite why yet. One of those, like if you just did that, that'd be fine, right?
Okay, so this would be the same too.
Yeah, none of these you're not gonna add two of those to
Okay.
anything. Yet. So hang on to that thought, but just do one at a time for now.
Okay. You got 5 bonds of that carbon. You got 4 bonds there with a positive charge. Perfect. You're running amok. Where's your product for all these? No, you don't end up with a positive charge, do you? Finish up the mechanism. You're fine so far, but finish up those last 3 there. Okay. That looks good. So what if I told you that was the only product? How can you explain that?
that was the only product. How could you explain that? What if this was the only product? How can you explain that? That's using resources. Oh my goodness. I'm just kidding. I don't want. Make sure you, because I'm going to ask you that, right? What did the book say? Click on the, open up the little tab thing there for chapter 18. 18, 17, 18, 8, 18, 9, 18, 10, those kind of things there. Probably 18, 10 might be really starting to show that stuff, yeah. Okay, so you got that one. So what about the other ones? That is not going to change, right? So show me the other ones. Looking over here. That was the only product that is. How could you explain that? Yeah, that's the stuff that you're missing. You were fine with what you had to do. Okay. Mhm.
That's what I was having trouble with, because I didn't know with this.
You just did it, huh?
This part. So how to, so right here, so now it's like closing the right.
And the example we did before this for this one, I might be sure to close and bring for that. Well, got good news, these are all planar, right? Remember, that's one of the definitions of an aromatic system, right? So no chair strikes. Although, if you want to knock yourself out, then,
I was trying to do a 2 lines thing.
yeah. Uh-huh.
I don't know what happens after that.
No, just changing the art.
No.
Oh, what is that? So it looks like we got the mechanism down. Is that mechanism going to be on the exam, you guys think? Yeah. Right. What's the challenging part? Maybe the rate determining step of that reaction. Right, formation, we should really say breaking open the aromatic ring, right? Not only do we have to break apart an aromatic ring, which sucks, right? We also form a carbocation, which sucks, right? You guys with me on this? What does it mean to be a rate determining step? Do not tell me what's the first thing that came to your guys' mind. I read your mind, Kate. Dr. H, it's the step that determines the rate. I know. Well, what does it mean, right? What does it mean?
It's just like the step that requires most energy and therefore the most time.
Mm-hmm. Right. And so if we want to favor a product, if we want to speed up a reaction, if we're going to make one product over the other, right? What are we really looking to control? The rate determining step, right? Our intermediate, got it? So why did I have you guys draw out all those mechanisms? Where does our answer going to come from? The intermediates there, right? You guys with me on this? Now I'm going to give you a hint. Those intermediates involve carbocations. And And what do we always have to pay attention to with carbocations? Shifts and rearrangements and all that stuff, yes. But what's the most important? Charge is very important. Resonance. Got it. Take a look and start to draw your resonance structures in all three of those mechanisms. I like this class because guess what I get to do? Sit here. You guys have to think. After age, you know it's a Monday. I think on Friday between hours of 3 and 3:15. Please come back to me then, right? You guys with me? So watch. Anytime I give you guys the impossible task, what am I really asking you guys to do? Think and break it down bit by bit, right? So let's assume that we have a carbocation. Yes. Can you guys draw a resonance? Yes, right? Should this be second nature at this point? Yes. Right, that's all you have to do, right? Draw resonance. Good. I'm going to give you guys another hint while you're working through this stuff. I want you guys to draw out these resonance structures. So if you guys need more paper, I will buy you all the lab, I will bring you all the paper you guys need, okay? And it'll even be the somewhat decent stuff. Okay? You guys with me? I don't need you guys to be shy about using paper. That's the big trick to organic chemistry, right? Don't be shy about paper. Now here's the trick. Got it? You guys with me on this? This is all starting to click together now. So draw me your resonance structures for the intermediates, for those three mechanisms, and then I'm going to wait to hear the right? I hope at least. I might just hear, oh. Resonance with your intermediates, right? Not your final product. So with the carbohydrates. That's okay. I'm just walking around. Just keeping an eye on what you guys are up to. Remember, draw your resonance with your intermediates, right? With your intermediates. With your intermediates. Show you guys something. No. No, not that one, not the way that you have it there. Yeah.
You could break it down though.
Can it? Good exam questions. Just 5 pages of resonance, that's it. what do they want to do with it? You've got infinite paper, so you can try whatever you want, right?
Yeah, look at everyone's out.
Buy you a nice one with like the pockets on the inside.
This one is not
Fine, whatever, jeez, trying to be nice.
it broke. The bottom part. So this one.
Well, let me put it this way, you could do that, but there'd be no practical reason, because you'd end up with a positive charge on the oxygen, right? It does, but doesn't move into the ring, though. It can't move into the ring. See, the nitro group's not the problem, right? What's the problem that we need to fix? And the nitro group is extremely stable. We don't have to worry about that. Problem is with our intermediate here, right? So let's just pick one of them. If you guys will indulge me, right? And if we just start with our Cl plus, right? Let's do this. Right? What's the problem that we have to fix in this intermediate? Is it the nitro? What's the problem?
Stabilizing
The carbocation, or all the resonance structures. Goodness. Fast class. Terrible. Awful. Death. Give myself some more space here. Magnificent. For all the resonance, right? Oops. See how it is. For all the resonance. That's your homework. Draw me the resonance. Okay? tell me why the one in the red is the only one that's going to lead to a product that forms. Okay? You guys with me on this? Red. Good? The answer is in the resonance structures. After you draw them, what do you have to do? I'll give you a hint. It's a big hint. The answer is already on the board. Got it? All you have to do is go, Or alternatively, you can go, and then say, I wonder what the book has to say about it, right? Good?